Introductions as people join.
Good.
So we just want to welcome you to the second talk of the GSN Symposium virtual series. Since the May Symposium got postponed, we figured we'd get some of our speakers to give a talk and take this opportunity to stay engaged in the community. Mike, Curtis, and myself are actually in charge of the technical program, so pulled from our own pool this time to have Curtis give a talk. Our next talk is going to be July 30th at 7 p.m. and that'll be Chris Henry. So if you will, mark out the fourth Thursday of every month for 7 p.m. GSN virtual series talk. We're keeping the information up to date online on our website, gsnsymposium.org. Chuck Thorman's previous talk and video is on there. We'll get Curtis's up there. So if anybody you know misses the talk, they're welcome to get to the recording on the website. And if not, we hope we can catch you live. Just a quick update on the symposium. We are doing our best to keep the technical program as intact as possible. We have some really great speakers lined up for the 2020 that are staying on for 2021. Inevitably, we will have a few speakers go away. So we're going to do a new call for abstracts. That'll be due September 30th of 2020 for those that are looking to get in with a poster or speaker slot, or even for those that didn't get a chance to write a paper this round who want to write a paper next round, or if you already wrote one paper and have another one in mind, we would love to have the information. We will be putting out some sort of volume for 2021 as well, likely mostly digital. So before we get started, we are going to ask everyone to turn off their video when Curtis gets started to get the bandwidth going. If you've got any questions, go ahead and drop them in the group chat at the end. We'll make it so everybody can unmute themselves and ask questions. I'll be monitoring the group chat, so if anything comes up, let us know. We've done a run through. This should go pretty well. So hang around after. Curtis is willing to answer questions. And a brief introduction on Curtis. For those of you that didn't catch his PhD, Curtis has just finished his PhD at UNR. He did his undergraduate at Oregon State University under John Dillis, and he did his PhD under Mike Russell and Philip Ruprecht at UNR. He's been studying the Phoenix porphyry skarn system and regional controls on gold-rich metallogeny of the Great Basin. After Curtis completed his studies in OSU in 2015, prior to joining UNR in 2017, Curtis worked in production and exploration in Newmont on the Northern Carlin Trend. Excuse me. Curtis is currently an economic geologist with Bronco Creek Exploration, focused on generative exploration for gold in Idaho and Nevada. So we just want to thank Curtis for sharing his talk, and he also has a paper in the upcoming volume, so keep an eye out for that. And with that, I'll turn it over to Curtis. I'm going to mute everybody, and if you make sure you flip your video off, that'd be great. So it's all you, Curtis.
All right, thanks, Molly. I appreciate that. I appreciate the opportunity. It's nice to digitally see a bunch of you that I haven't seen in quite a while. Hope there's some new faces that didn't catch my dissertation talk. This is relatively similar, a few differences here and there, but generally the same story. So if you didn't get a chance to ask questions when you watched that, happy to hang out afterwards and talk for a while. So go ahead and share the screen here. Okay, and full screen. Okay, Molly, does that look all right?
We've got a few of those blue boxes. Let's try and go through a slide or two, and if we're still getting those, we'll try another option.
All right. Interesting. Okay, so the title of my talk, as Molly mentioned, is it's the relationship between Eocene magmatism and gold mineralization in the Great Basin. This is something I've been working on for quite a long time, more or less following up some of the early work that Mike Russell and others did in the 90s and 2000s that really firmly established this link between Eocene magmatism and the big sweep of gold mineralization found mostly in north central Nevada, but also in parts of Utah as well. So we looked dominantly at the Phoenix-Fortitude skarn system, world-class, actually the largest and highest grade gold skarn in the world. It's in the same age and associated with the same intrusions or same age of intrusions as the Carlin trend. So we wanted to look at that where it's clearly linked to mineralization, and then step out from there and look at sort of the regional picture. So, and I just want to thank Mike for advising me and for getting this project going, and then Philip Rupert as well. We did write a paper for GSN, and then we'll also have a number of other manuscripts coming out wherever they accept us, so hopefully sometime soon. And, all right, the box is all right there, Molly?
I'm still seeing it, but it's not interfering, so you're good to go.
Okay. Interesting. Okay, so I broke it up into 3 parts. The first is just the geologic and metallogenic framework, and then we'll jump into what we actually did, focusing on Eocene magmatism, talk quite a bit about the Phoenix-Fortitude skarn system and the intrusions associated there. And then we put together a model, genetic model, and then how you might apply it in exploration for Carlin-type deposits, as well as gold skarns and other terrains that show similar characteristics. So we'll kind of step through it in that order. And just to begin, we'll look at the Great Basin broadly. So here's a hillshade. You can see Nevada outlined nicely there. Here are just all the major deposits and districts within this region. You know, many of you are much more familiar with a lot of these than I am. But if we break them up by age and different metallogenic event, we have multiple different sweeps of mineralization. So we have the Jurassic Arc in green, back arc, Bald Mountain, Yarrington, the Cretaceous, potentially back arc, but mostly sedimentary derived melts, Robinson and others. What we're focusing on are the gold stars, which are the Eocene arc-related mineralization or deposits. And then from there, we have a Oligocene, ignimbrite flare-up related at Round Mountain, as well as Miocene, the ancestral cascades, mostly the Walker Lane, and then rift-related epithermals with some younger amagmatic rift-related epithermals. So a broad spectrum of different deposit styles, and again, we're just focusing on the Eocene. So the really interesting thing about the Eocene and why we want to focus on it is it accounts for about 80% of the total gold endowment of the Great Basin, which I've been studying, looking at Eocene magmatism for a good 5 years before I realized that. It's pretty amazing. But it actually also contributed over 50% of the silver, 50% of the copper, and 50% of the molybdenum. It's pretty phenomenal. And when you look at it in more detail, it actually is sort of bimodal, as a lot of us probably know. In Utah, they're much more gold rich, or much more copper rich, versus Nevada contributes most of the gold mineralization. And so if you just look at it from a percent perspective, almost 100%, 99% is of the copper is from Utah, and about 80% of the gold is from Nevada. So we notice that there's just this bimodal distribution of the different styles of the endowment of metal and also the styles of mineralization. And so if we look sort of in this box here, looking just at the north central Nevada gold story, we'll kind of provide a little context here. And most of these deposits are sediment hosted. There's 4 dominant styles that we sort of broke apart that lie along a relative temperature spectrum from hot to cold, and this is just showing you over here on the left, relative temperature, and that's just moving away from the intrusion. So the highest temperature shown in red dots on the map, and for scale, Elko is right about here. There we go, laser pointer. Elko's here, Battle Mountain is here. So clustered around mostly the Battle Mountain district, but also in the Shoshone Range and at Cove McCoy. These account for about 9% of Nevada Eocene gold production. These are reduced gold skarns dominantly with calc silicate alteration. There's major pyrrhotite, pyrite, and chalcopyrite as well, but generally a reduced assemblage of sulfides and oxides. And overall porphyry type fluids, hypersaline, high temperature, but the big story is that they're reduced relative to other intrusion-related systems in the Great Basin. And moving a little bit cooler from there, the distal disseminated gold deposits, which also account for about 10%. These are intermediate temperature associated with quartz-sericite pyrite, arsenopyrite assemblages. They're spatially associated, as you can see, where they cluster in orange dots with gold skarns. They, in some instances, especially at Phoenix, they are the more distal portions of that. You can actually see the zoning. There's several deposits, but all but two have gold-only production. There's generally a higher base metal content with lead, zinc, and some copper, silver as well, but arsenic, antimony, trace elements along with it. And again, commonly pyrrhotite with arsenopyrite, so more of a reduced style mineral assemblage. And then we jump to Carlin-type deposits, which account for about 75% of the total Nevada Eocene gold production. Those are the yellow dots here, clustered in the trends that we're all relatively familiar with: Carlin Trend, Battle Mountain Eureka Trend, Getchell, and the Great Canyon Independence Range. And there's many deposits, but the key is that there's really only 3 world-class districts that are known currently, and that's the Northern Carlin Trend, or the Carlin Trend, the Cortez District down here, and then the Getchell Trend up in here, Turquoise Ridge and Twin Creeks. Dominated by arsenium pyrite, hosted in calcareous carbonaceous rocks, gold, arsenic, antimony, mercury, thallium, and barium associated geochemistry. And the distinctive alteration is carbonate removal with jasperoid as well, but dominantly carbonate removal. And the grades are quite variable, but high enough grade to mine underground, approaching an ounce per ton in many places. And the fluids where they've been studied in detail are distal, appear to be distal, lower temperature, and the paleo depths are between 1 and 2 kilometers. But dominantly the fluids are meteoric with some components of magmatic fluids, possibly meteoric or metamorphic, but dominantly meteoric hydrothermal systems. And then the shallowest are what actually Elizabeth Hollingsworth, who's another PhD student of Mike's at UNR, did some great work in the Southern Carlin Trend, breaking this class apart. Account for about 6% of Nevada gold production, but these are what we're calling paleosurface Carlin-type deposits. But the key characteristic is they're very similar to Carlin-types. They have a higher silver content, and they appear to be, in some cases, mineralized the paleosurface, so shallower, and something like less than 500-meter paleo depths in most cases. But you see some distinct differences between these and Carlin-types, with some coliform quartz, barite, stibnite, cutting jasperoid, and then barite and quartz overprinting a jasperoid bladed. And that's characteristics of the Southern Carlin Trend down here. And so we have these 4 main deposit types in the general sense: low to high temperature. So at the surface, paleosurface Carlin-type gold, intermediate Carlin-type gold, classic style, distal disseminated gold, and then reduced gold skarn or porphyry, in some cases if it's hosted within the intrusion. The deposits are gold dominant in all cases, base metal and silver poor mostly. Deposits formed about 42 to 34 MA, coeval with and co-spatial with a sweep of magmatism that we'll talk a lot more about going forward. And the differences reflect a multitude of different factors, but it seems to be a key control is the distance from the intrusion and the temperature of fluids. And where they cluster, it probably reflects variations in exposure level. And that largely the Battle Mountain District provides the best example, where you see in the footwall of one of the major faults that has at least 1 kilometer of throw on it, you have dominantly porphyry skarn systems, and then in the hanging wall, about 1 kilometer closer to the paleosurface, you have distal disseminated deposits of Lone Tree and Marigold and others, and there's a few other examples of that. And interestingly, the division between the shallowly paleosurface, Alligator Ridge, Southern Carlin Trend, and the deeper formed Carlin-type deposits of the Carlin Trend, Cortez, and Eureka, as well as the intrusion-related, clearly intrusion-related systems, are separated by the Roberts Mountain thrust fault. And so potentially that's a strong control, maybe on how deep you see in the crust, but also, as many people have postulated before, as a trap to fluids to keep them deeper down. And so there's two styles that are clearly intrusion related that I already briefly mentioned, and that is the porphyry skarn, reduced gold skarn systems, and the distal disseminated gold. There's almost always intrusions associated with that in the same structures and areas that host mineralization. But Carlin-type and paleosurface Carlin-type gold, it's a little more complicated. You're more dilute, more distal. And in some cases, there's associated Eocene dikes, and the ages on mineralization overlap with associated magmatism nearby. But it's more difficult to draw that connection. And so if we look just at the Eocene high temperature, because it sort of removes that variable of distance away from intrusions and the influx of meteoric water, the fluids and the metals are unequivocally related to Eocene intrusions, and that's an important point. And so here we're just looking at the map of the northern Great Basin, and we're highlighting Phoenix-Fortitude, which is the gold skarn, reduced gold skarn, and then Bingham, which is a classic porphyry copper gold system further over in Utah. And so if we just compare the two, you can see in high temperature veins, these two photos are a nice example. This is Bingham from Patrick Redmond's work that shows A-type veins, quartz, chalcopyrite, and then some quartz bornite magnetite veins. Classic of a typical porphyry system, approaching 8% copper with half a gram to a gram gold in the high grade portions. And then in contrast, if you look at Phoenix-Fortitude, where you're in the similar K-silicate alteration assemblages, here's an example of a quartz bismuthinite native gold vein. Commonly, they're quartz pyrrhotite, chalcopyrite, sometimes with bismuthinite as well, and arsenopyrite, but you don't see this style of assemblage in most classic or any classic porphyry systems. So that was one early observation that something different is going on here. And they're both the same age, 38 to 39 MA, and associated with the same sweep of magmatism. They're both gold rich, but the gold copper ratio is really different, about an order of magnitude different, about 4 at Phoenix and about 0.4 at Bingham. And they are both spatially associated with distal silver, lead, zinc. At Phoenix, they're more gold rich, the distal portions, and then also Carlin-type or Carlin-style occurrences with jasperoid and some decalcified zones. At Bingham, there's over 1 million ounces of Carlin-type ore distal to the main porphyry system. At Bingham, the mineralization is dominantly oxidized, and at Phoenix-Fortitude is dominantly reduced. That would be how you generalize and summarize it overall. And at Bingham, the magmas have been extremely well studied and are highly oxidized, typical of most porphyry-related magmas. And at Phoenix, there's been various studies that sort of argue one way or the other. Earlier studies argued it was more reduced, and then later argued it was more oxidized. So it's kind of a question mark, and that's something that we wanted to look at here. And so the big question, what we really wanted to try to sort out is what is the difference? Since these are both magmatic hydrothermal fluids derived directly from an underlying magma, they interacted with some crust, but probably minimal compared to Carlin-type deposits and more distal. So something from, likely from the magmatism is controlling this difference. So that's what we wanted to look at in detail. And so if you look at the east to west story, what else changes besides the mineralization? And the dominant change is the thickness and the style of the shallow crust. So as you move from east to west, it's a thickening sequence of the Paleozoic passive margin. And the really key characteristic that changes as you go westward is you're getting closer to the basin and more anoxic environments, and the sediments get more carbon rich. And carbon is a really strong reductant for magmas and fluids. So you would predict that if you put the same magmas up through Utah versus Nevada, you'd get a more reduced magma within Nevada. And that has important implications for gold and copper in melts, but also in fluids. And so that's a really key part of the story, is that the crust is dramatically different east to west, both in thickness and in the reducing ability. And so here, if we look at same map, north central Nevada, here's Salt Lake City and Elko. Just looking at the distribution of Eocene magmatism and deposits again. So here's the Eocene arc. It's been extended 50 to 100% depending on where you're at. So it looks less like an arc and more like a shotgun pattern. But largely these are 42 to 34 MA intrusions and volcanics before you before you become more explosive and the nimbrite flare-up starts up, moving sort of in this direction into the Oligocene. So these are dominantly andesite, dacite, with some rhyolites kind of throughout the province. And in general, there's a south-southwest rollback, a younging from about 42 to 34. And that's related to rollback of the flat slab. Laramide compression likely caused flattening of the subduction angle, and it sometime between the Laramide and the Miocene, it rolled back to present geometry. So it moved through this part of the world at about 42 to 34, causing melting, abundant melting. And then here's a couple lines that show some important boundaries. So one, this is from Harry Cook's work. This is the easternmost boundary of the platform, the slope and the platform shelf margin. So everything westward would be considered dominantly sloped to basin, so more carbonaceous, and moving eastward, it's dominantly platform, cleaner limestones. As you move further east, you get more quartzites and more clastic rocks, but that's a general difference. And the key is that it's in general. There's a lot of variability as you move forward, but overall, you see more reducing rocks west of this line. And then here's the strontium 706 line, which just marks the edge or approximates the edge of the North American craton and the Paleozoic passive margin. So as you move westward, it's mostly younger rocks, but also accreted terrains, so different crustal composition. And here's where the deposits we've been looking at plot relative to these lines. As you can see, most of the major gold deposits and gold trends occur between these two lines. There are other occurrences, Long Canyon out here, Kinsley, and a few others as you're east of the line. But dominantly, the bulk of the mineralization and metal endowment is between these lines in terms of gold. And then if you're looking at the eastern portion, there's several major districts, but the three shown here are Bingham, Park City, and Tintic. And these are porphyry-related districts, only major porphyry copper deposits at Bingham that's currently known, but large silver, lead, zinc, carbonate replacement deposits and related epithermal systems. And so again, it's shown just in the color coding. It's dominantly copper, silver, lead, zinc rich in the east and gold rich in the west. And so here, this is just compiling a lot of previous work. Here showing Greg Earhart and some of his students' work looking at isotopes in magmas. So here, it's just kriged up values. The darker the color, the more sedimentary influence on oxygen isotopes. So you can see when you're westward, in the west, you see more influence of crust in the oxygen isotopes. And then if you look at sulfur isotopes, it's a very similar story. The darker the colors, the more sedimentary sulfur the magmas have taken in. And then looking at the aluminum saturation index, which is a proxy for the amount of crust that's been assimilated and type of crust. So similar story to the west, you see much more of an influence of the shallow crust. It could be because it's thicker, but it could be also that it's different composition. And so here's a nice cross-section from Tomlinson's work in the 90s and published in GSN in 2000. So this is scaled to the map. Here's just longitude, and then this is the oxidation state relative to an experimental buffer called nickel-nickel oxide. And these are log units, so it's a pretty significant difference along the black line. So the black line is oxidation state, increasing upwards, and the orange line is just whole rock copper, and these are unaltered lavas of the Eocene arc. And so you can see there's a nice correlation as you go eastward, just looking at lavas of increasing copper and increasing oxidation state. And that has been shown experimentally, that relationship has been repeated, that as you get more oxidized, you can, more copper is soluble in the melt. And then as you get into this sort of slope to basin setting, there's a big dip in oxidation state, multiple log units here, and then a few upticks to +2, and then back down. So there's a major difference by multiple log units sort of right around the longitude of the Carlin trend, which is a pretty interesting observation. So this is what we sort of were going off of when we first started this study. We'd compiled all this and seen that there's a big difference in the metals and a big difference in the unaltered lavas of the Eocene, as well as some of the intrusions. So now we'll jump into what exactly we did, looking at the Eocene arc and its associated mineralization. And so what we know, or what we knew starting out, is Eocene magmas, just in general, were particularly fertile. They produce large mineral deposits of multiple styles and world-class affinity. So something was special about the Eocene arc to begin with. And as you move east to west, the shallow crust becomes more reducing, and it also becomes thicker. The Eocene volcanics show a similar trend, becoming more reduced as you move westward and showing more of an interaction with the crust through isotopes. And then the last key thing, I won't belabor too much, but in general, the different styles of mineralization and the associated metals are bimodal from east to west. So copper-rich in the east dominantly, and gold-rich to the west. And you also see differences in the mineral assemblages, from more oxidized in the east to more reduced in the west. So our primary question was, does the magmatic redox change in ore-related intrusions east to west? So do we see that same shift to more reducing oxidation states as you go westward? And if so, what implications does this have for the gold-copper ratio, sulfur in magmas, and in general, the roots of a gold metallogenic province? So we took a scaled approach, spent a lot of time at Phoenix, mapped a whole bunch of high wall, had a lot of fun doing that. And we really focused on putting together the time-space framework. So what happened first, what happened second, in terms of intrusion, veining, and how the system evolved through time. And then we did quite a bit of analytical work to define the magmatic evolution, in particular, how the oxidation state changed through time. And then we expanded it. Once we figured out some methods that seemed to work pretty well, we expanded the study to a regional sample suite, looking at select intrusions just directly related to mineralization. We applied those same methods. And then we took these data and then we placed it into this geologic context of the crustal composition. And the main goal of that was to establish a regional exploration model that you could port to different areas of the world that have similar characteristics of reducing crust to look for intrusion-related and Carlin-type gold. So starting with Phoenix, here's what we looked at in general. So here's the same blue and red line. The dark colors are Eocene volcanics and intrusions, and all the stars are what we sampled. So Bingham, Stockton, and Tintic, as well as San Francisco district, which actually turned out to be Miocene. Some of the maps had it as Oligocene, so we thought it was part of the suite, but it's an interesting part of the story anyhow. And in Utah, we looked at the North Carlin trend, the Beast Rhyolite, Deep Star, and Betsy, the Betsy Post dacites, as well as Bullion in the Southern Carlin trend. The Granite Mountain, unrelated to mineralization directly, but a deeper hypothesis, probably from some more related intrusions. Hilltop, and then a number of intrusions within Battle Mountain, notably the Phoenix-Fortitude system. So we, again, did a whole bunch of mapping at Phoenix, did some age dating, and established the framework. And our primary methods were laser ablation on zircon. So we really focused on zircon because everything was heavily altered, every rock that we looked at. Zircon is robust, and we also looked at apatite as well because it shows similar characteristics of not being too affected compositionally by high temperature fluids. So we calculated uranium lead ages and trace in rare earth elements, so about 800 and some analyses. And then we utilized a method called Zanes, which is sort of like a high energy XRF, but it's small spatial resolution, about 3 micron spot size, so you can be really precise with it. And the critical part of that is you can tell how much of a certain oxidation state of an element there is. So you could do iron 2+ versus iron 3+. So you can quantify how much iron 3+ versus iron 2+ is there. Zircon doesn't take in iron, but it does take in cerium, which can be a 4+ or a 3+, depending on the oxidation state. So that was one of the main proxies that we used based on other people's work as a proxy for oxidation, because in a more reduced setting, you should see more cerium 3+, and in a more oxidized setting, you should see more cerium 4+. And then from there, we looked at apatite, in particular using the microprobe to detect sulfur and chlorine, fluorine as well, but mostly sulfur and chlorine, because we wanted to see how that changed throughout the province, because sulfur can similarly be in a number of oxidation states, and it substitutes into apatite better as sulfur 6+, so as an oxidized state, versus sulfur 4+ or sulfur 2- in the reduced state of sulfide. So we wanted to see what story could be told from those data in comparison to the oxidation state, since it is linked. So starting with Phoenix, here's a map of Phoenix. This is the alteration. Won't go into too much depth, but the red circles are showing 3 different magmatic hydrothermal centers we worked out, a number of porphyry dikes that are earlier than the main intrusion, which is this pink blob here. The alteration colors, brown is biotite hornfels and dominantly a sandstone unit, and argillites as well. Dark green is skarn, pyroxene dominant. Garnet skarn is in red. There's not much of that left. Most of it's mined out. And a bit of actinolite chlorite in the bluish green color here. And then the broad north-south trends of yellow are structurally controlled quartz-sericite pyrite arsenopyrite, which is analogous to other distal disseminated systems in the Battle Mountain District and elsewhere in Nevada. And so summarizing the time space, we kind of broke it into 3 different categories. The P1 stands for the first porphyry. There's a number of these intrusions, and this is kind of what they look like. This is a thin section billet for scale, about 3 centimeters tall, something like that. But quartz hornblende, plage, and biotite ferric, and these are clearly spatially associated here in these 3 circles. I've just enlarged them to show you, with anhydrous skarn, prograde garnet pyroxene, with potassic alteration in igneous rocks, but it's dominantly in the sediments, but very strongly associated, in particular with proximal garnet. And then the copper canyon granodiorite porphyry, which is this main stock, and then the sunshine porphyry here, which is a related apophysy. These are different compositionally, more evolved. They're large centimeter scale quartz phenocrysts, with some megacrystic case bar, but it's not clear what mineralization, if any, this is associated with, but likely some biotite hornfels, more thermal style metasomactism. And then a later series of P2 porphyries. If you're familiar with the Battle Mountain District, the Virgin Dike is part of the P2 porphyries, and that would be this dike here, filling a major north-south fault. And these are very distinct from both P1 and most of the copper canyon granodiorite, with these large multi-centimeter case bar megacrysts, big quartz phenocrysts or xenocrysts in some cases, hornblende, biotite, and plage. And the interesting thing about this stage of magmatism is it fills the same structures, and it's strongly associated spatially with where you get QSP, or quartz-sericite pyrite, arsenopyrite, and actinolite skarn. So similar, the same fluids, just actinolite skarn being over the top of earlier pyroxene skarn. There's a really nice spatial association with this, and the P2 porphyry dikes are always mineralized by this later event, but not by the earlier event. So there's a nice time relationship there. And so how these veins look, it's sort of detailed maps or figure, but in general, quartz-rich veins in the earliest. So this would be stage 1 in the top, the P1 porphyries. So moving to the right, the veins get later and they get more sulfide-rich. Many different events. This shows it nicely of A-type, AB-type quartz veins with pyrrhotite, chalcopyrite, and then the later veins start to be more rich in pyrrhotite, or pyrite with chalcopyrite here, and then a bit of magnetite as well. But almost always in clastic or aluminosilicate rocks, biotite case bar is the alteration assemblage, and in calcareous rocks, it's pyroxene with some garnet locally, but mostly pyroxene. And if we look at the later veins, much more sulfur rich, sulfide rich. Here's a nice example of an arsenopyrite chalcopyrite quartz vein cutting an earlier A vein here. There's actually muscovite illite alteration over the top of biotite. So that's a nice relationship there, showing these are later. And you see that quite a lot. The earlier AB veins are cut by these, which is pretty typical in porphyry systems. What is non-typical is the abundance of arsenopyrite. And here's another example. This is from the Virgin Fault Zone. It's about a 20-foot wide zone of quartz-sericite pyrite arsenopyrite replacement. And these veins are almost all rich in arsenic, antimony, bismuth, and tellurium. Some base metals, but mostly that metal sweep. And there's some interesting breccia textures here with siderite in a number of places, but dominantly more sulfur-rich or sulfide-rich and associated with sericitic or muscovite illite alteration. And here's a diagram to just summarize that. There's a lot going on in it, but in general, we have the time early to late intrusions moving to the right. So there's likely a large batholith here. In a few places, there's xenoliths, actually in some of the later dikes of this, what looks like a granite batholith. Actually a lot like the Granite Mountain intrusion in the Shoshone Range to the east. So intrusion of the batholith, and then here we just have depth going down. This is the Eocene paleo surface up here, and then this is the current surface. So Phoenix is probably formed between 1 and 2 kilometers depth, something like that. So the P1 porphyries intruded, fluids were higher temperature at this level. And so it's dominantly pyroxene skarn, 5 to 400 degrees C styles of mineralization. Copper Canyon stock intruded. Again, there's not any obvious relationships between mineralization with that, but it's the volumetrically most important intrusion. And then the later P2 porphyries probably were derived from deeper down in the batholith as the batholith cooled, and that allowed fluids to cool more by the time it reached the same level as the earlier P1 fluids. So it's 350 to somewhere in that ballpark to stabilize sericitic alteration. So this is kind of that relationship of this overprinting of a lower temperature fluid, still magmatic hydrothermal, but it had more crustal column to cool over the top of the earlier anhydrous skarn. And I guess just showing that there. And the key takeaway is that there's just a lot of overprinting and zonation, but in general, it's just an earlier sequence of anhydrous pyroxene garnet skarn that's overprinted by actinolite chlorite, as well as sericitic alteration on top of biotite case. That's the dominant overprinting relationship. And here's what some of the geochemistry looks. These are plan maps, blast holes of the Fortitude area. So the Copper Canyon stock on the map above sits right here, just to the south of the blast holes. And here you can see the major structural controls. This is gold grade. Yellow is, anything hotter than yellow is greater than a gram. And so here would be the lower Fortitude gold skarn. The assays are not available. There's 11 million tons at 5 grams gold. That's the highest grade gold skarn body in the world. And so here you can see this nice relationship of P1 porphyry outlined here. And this is all garnet pyroxene skarn mineralization, just spatially associated with that. And then the Virgin Fault here is filled by the P2 porphyry and associated QSP arsenopyrite mineralization here. And then just looking at the copper briefly, you can see the zonation. By the time you get about 500 meters to 1,000 meters north, you more or less lose all the copper. The fluids are too cool to transport much copper. And then here's what the district scale zonation looks like. An internal gold-copper skarn system, distal gold-rich skarns like the lower Fortitude skarn. And then as you go to the south, it goes undercover, so we don't really know what's there. As you go north, it's the Galena silver lead zinc district, mostly carbonate replacement deposits and vein structurally controlled Galena sphalerite veins. And then as you go north from there, in the sandstones, there are antimony, gold, arsenic, bismuth, tellurium, quartz veins. Here at these X's are the prospects. And then as you're in the Antler Peak limestone, it forms jasperoids that are rich in gold and arsenic. There. So that's district scale zonation. So now onto the intrusions. Looking here at the, we broke it apart into, again, into the P1 porphyries, the copper canyon granodiorite, and the P2 porphyries. And so looking at zircon chemistry, here we have hafnium on the X and the uranium-ytterbium ratio on the Y. And increasing hafnium, increasing uranium-ytterbium is a proxy for melt differentiation, so a more evolved melt. And the darker colors are the P1 porphyries, the greens dominantly. They overlap a decent amount because these are mostly granodiorites compositionally. But the later P2 porphyries are in the pinks and reds. They extend to a much higher uranium-ytterbium ratio, suggesting they're more evolved. And we know this also from the modal mineralogy, being K-spar, megacrystic, and such. The copper canyon stock is just right in the middle in yellow here, so some combination there of the two. And so here's a plot showing the oxidation state that we calculated from zircon composition using a brand new formulation from Lux and others. It uses the uranium, the cerium, and the titanium content to give you a calculated oxidation state. So here's temperature, so decreasing to the left, and then here's oxidation state relative to oxygen fugacity moving up, and these are log units. So here we show the darker colors again are the P1 porphyries, showing higher temperature zircons, but also more oxidized in some cases, extending to a higher oxidation state overall. And then the P2 porphyries here evolved to, in general, a lower oxidation state, about a log unit below. We'll use the FMQ buffer. That stands for the phalite to magnetite quartz reaction line. That's a pretty common one in the literature. And it'll just be log units from that. So overall, the oxidation state of the Phoenix magmas, if you just took an average of everything, is FMQ minus 0.13. And there's something like 180 data points in there. There's a decent amount of data to take that average from. But in general, the most zircons plot within about 1 log unit of FMQ, so plus or minus 1 there. The earlier high temperature zircons show scattered, but some more oxidized zircons, and the later zircons seem to be more reduced in a lot of cases. And this does contrast with some previous work suggesting the magmas are oxidized. Caleb Ping did a really great job studying this in the greater Battle Mountain district. He observed magnetite plus titanite assemblages, which suggests multiple log units above the FMQ. But it could be that some of the earlier magmas were more oxidized and it got more reduced through time. And so if we look at the Zanes data, so this again is the cerium-4, cerium-3 ratio, and it's directly linked to the magmatic redox. So here, this is the hafnium content. So as you move to the right, you're getting more evolved. And then this is the percentage of cerium-4 to cerium total. So 100% is 100% cerium-4, and 60% is 60% cerium-4, 40% cerium-3. So getting more reduced as you move down this plot. So you can see nicely that the most oxidized looking zircons from Zanes data are the green. You do see some scatter, and it's important to note that because zircon, the later intrusions are almost always going to have earlier crystallized zircon from the P1 suite from the underlying batholiths. So you're definitely going to see scatter there. But overall, the green and blue zircons appear to be more oxidized, particularly the Fortitude porphyry, which is P1. And then as you get more evolved in the reds and pinks with the P2, the virgin porphyry, they're more reduced looking at the cerium data. And this is plotting just histograms of all the different intrusions, same color scheme. So the darker the color, the earlier the intrusion. These are just frequency diagrams here. And overall, you see this trend when you look at the histograms of decreasing as magmas become more evolved, decreasing in oxidation state, or cerium-4, cerium-3. And then here I've just plotted up the gold and copper, the relative contribution of the metals. The earlier intrusions are associated with gold and copper mineralization, whereas the later you see a divergence of essentially 0 copper mineralization and dominantly gold. And that's likely temperature controlled, but also could be somewhat related to the differences in redox between, especially if you look at the green and the pink. There's a very large difference between those in terms of measured cerium 4, cerium 3. Okay, so now we're going to step out to the regional story. We analyzed 33 different intrusions, 33 new ages, uranium lead, all generally overlap, nothing really new here. Nevada are mostly around 38, 40 to 37, and the Utah intrusions are younger. The one new thing that came out of the age dating was the Miocene age for the San Francisco quartz monzonite porphyry, but overall it overlapped with previous ages. And so looking at the regional picture, we know, or at least it looks like Phoenix-Fortitude is moderately reduced, and it shows that reducing trend through time. And so if we look at all of the intrusions, here again is temperature on the X versus oxidation state increasing vertically. Red, this is going forward, red are all Utah samples and gold are all Nevada samples. And I'll use that color scheme going forward. So you can see very clearly there's two distinct populations. There is overlap, there's always scatter, but the red samples are much more oxidized than most of the Nevada samples, especially the Phoenix samples. And if you look at it on a histogram and you look at averages, here's oxidation state, so getting reduced to the left and oxidized to the right. It's about 2 log units, or about a little over a log unit difference in average between the two. And then Phoenix-Fortitude is another half log unit less than the Nevada. And there's something like 500 data points there. So there's a lot of measurements to support that trend. And it looks like in Utah, there's a trend of actually getting more oxidized through time from the big clustering of data points from all the different intrusion centers are right around this FMQ to FMQ plus 1, or right at NO. And many of the later rhyolites, which are these intrusions here, are FMQ plus 1 to 2 pretty consistently. So there is that trend. And then the Nevada's intrusions show a much different trend of getting more reduced through time. So down to FMQ minus 1. And again, these are log units, so it's pretty significant. And here's what the intrusions look like, just broken apart different centers. Nevada is on the bottom in the darker colors, and Utah is on the top, just showing that difference there. And then here, getting back to the Phoenix versus Bingham story, again, the same age. This is all of the Bingham zircons here, and then these are all the Phoenix zircons color-coded to more evolved through time, the hotter the colors. So you can see there's just almost no overlap. And if you look at the standard error of this analysis is about 0.6 log units, plus or minus. So even with that, there's still, there is more overlap, but not much, especially in the higher temperature parts of, at least the higher temperature zircons from Bingham. And then if we look at all of the cerium zanes data from the regional data set, you see a very similar story. So here, this is actually 100 all the way to 0. So 0 is 100% cerium 3+, so completely reduced cerium. And Nevada is you only see really less than 40, but down to 0 in the 0% cerium 3+ in the Nevada samples, whereas most of and all of the Bingham samples, or the Utah samples, are greater than 60, and most greater than 90. So a distinct difference there. And here it is plotted as a histogram. So oxidized cerium here, reduced cerium here, and every category or bin less than 70, Nevada's more abundant, and every category greater than 70, Utah is more abundant. And it's roughly the same amount of samples, about 160 from Utah and from Nevada of the cerium zanes. And again, more histograms just showing that same point, that you see a full spread from 0 to 100 in Nevada, and you don't see that in Utah. Especially when you look at the more evolved intrusions, the rhyolites, so Battle Mountain rhyolite, porphyry, bullion rhyolite, as well as the deep star rhyolite, all show the majority of these 0% cerium 4+, or 100% cerium 3+. Whereas Tintic, the Swansea rhyolite, similar SiO2, a little bit less, but almost all oxidized in terms of cerium. So very different story there. And here we'll just touch on the apatite geochemistry really quick. This is chlorine on the X, and this is sulfur measured in apatite. And so same color scheme, yellow versus red. So Utah, the red samples, the averages are plotted here. There's not much overlap. The apatites from Utah are much more sulfur rich, as you would expect. Within a more oxidized setting, you get more sulfur 6+, which is more, which is happier in apatite, versus Nevada, which you're probably in a sulfur 2- dominant regime, and the majority of your samples are going to be relatively copper or sulfur poor. And if the detection limit actually of this analysis is about 0.01. And if you just look at below detection limit analyses, there's about 150 of the analyses out of maybe 400 were below detection limit for Nevada, and only 13 from about 400 from Utah were below detection limit. So there's a major difference between the sulfur content in the apatites, and whereas the chlorine is not as, the difference is not as great. And here are just the different data sets spread apart. Okay, so the takeaways, I think the key is that Eocene magmas probably were initially oxidized. I think that's true for all of the Great Basin. You see that in the earlier higher temperature zircons all throughout Nevada, and then consistently in Utah as well. In Nevada, the more evolved intermediate to granodiorite to granite compositions are more reduced by about 2 to 3 log units, and this plot is showing that with oxidation state here. And then this is just the different intrusions we looked at. Gold is Nevada, Utah here. And you can see this is with a standard error plotted, plus or minus 0.6 log units. But Utah, the majority of especially the mineralizing intrusions at Bingham, are much more oxidized versus Nevada, it's more reduced. And so it looks like Utah, it retains its higher oxidation state or possibly becomes more oxidized through time. And Phoenix is about 2 to 4 log units lower in FO2 in oxidation state than Bingham. That alone can explain the differences in mineralization style as well as the gold-copper ratio. This is a plot from Zoltan Zajak's work, experimental work showing this is just magmatic gold-copper ratio at different oxidation states. So the peak gold-copper ratio, so the highest gold content in relative sense, is in this MQ +1 to -1 range here. And then as you get more oxidized, it drops off because gold really likes reduced sulfur. And this line shows the general reaction line between sulfur 2- to the left and sulfur 6+ to the right. And that's an oxidation reaction. And so there's a really nice correlation in all the experimental data between gold solubility and sulfur 2- content and the oxidation state being right in this sweet spot between +1 to -1 FMQ. So the takeaway is, or another key part of it is Eocene magmas in Utah have sulfur-rich apatite, so they're probably more sulfur-rich, which is a function of the oxidation state. Again, sulfur 2- to sulfur 6+, and that can also explain the higher sulfidation states of some of the mineralization. There's just more sulfur available to fluids. So the key takeaway from a magmatic perspective is the differences in oxidation state will give you a difference in in a volatile sense, the H2S or the SO2, so the reduced versus the oxidized sulfur. And that will be imparted on the magmatic hydrothermal fluids. So you're going to have different sulfur volatiles in your fluids. Okay, so we'll just go quickly through the genetic model. So just touching on this one more time, this is a generalized cross-section from east to west in the Great Basin. We have Utah porphyry systems here in the limestone, sandstone, the shallower water, shallower crust part of the past margin. And then as you move westward, the reducing potential increases, you get more organic carbon, especially in the slope to basin settings. And the zircon data of magmas match the same trend. Magmas get more reduced as you go west. And And you would predict just from a redox standpoint that you would get oxidized porphyry copper gold systems in the east, and you would get reduced intrusion gold systems or skarns, as well as gold-rich distal systems in Nevada. So here, looking at a cross-section, this would be your primitive magmas, 25 kilometers depth per scale, so looking pretty deep. And this is just in the north-central Nevada, the darker colors insinuating the more organic carbon as you get to the upper 10 kilometers, and then north-central Nevada, a more oxidized type setting. Large batholith development, and likely in this area is where you're assimilating some reduced crust and changing the oxidation state to more reduced, probably not considered a true reduced magma, but more reduced than in Utah. And that again is changing the H2S SO2 ratio. And the changes in oxidation state result in gold-rich magmatic hydrothermal fluids in Nevada and copper-rich in Utah. And that's because of more of Zoltan-Zajak's work. This is showing oxidation state versus gold. This is actually partitioning, so how much gold goes into the fluid from the melt relative to oxidation state. And similarly at this, this real FMQ plus 1.5 to minus to around 0, there's a strong peak, almost 100 times more gold will go into the fluid than if you're at an oxidized scenario. And so here's just showing the oxidation state versus the gold copper ratio, or the copper gold ratio, sorry. So the copper gold ratio increases as you get more oxidized. And that's again a function of oxidation state. And a really key takeaway of this as you translate it to the lower temperature environment, gold solubility is highest in the reduced type setting and the near neutral pH. So a reduced carbonate crust is about the optimal way to transport gold. And if you have more H2S or more reduced sulfur in your initial fluid, it's much more effective at getting gold to low temperatures because gold bisulfide, reduced sulfur complexes are stable to low temperatures, and that's the dominant mechanism of gold transport in Carlin-type. Whereas in oxidized settings, when you're gold chloride dominant, those are mostly stable to 400 degrees or greater. So you see gold precipitating in higher temperatures versus lower temperatures in a more reduced type setting. And that may explain why the world-class Carlin-type deposits are in Nevada related to these intrusions in some cases, because there is more reduced sulfur around to get gold out of the high temperature. So we just look at the different styles of mineralization in this. So in the Utah scenario, the oxidized porphyry coppers, distal CRD deposits, and then potentially Carlin-types, because there is always some H2S around. In the vertical sense, high sulfidation epithermals, you see much more advanced argillic alteration, likely because there's more sulfate, which dissolves in groundwater and creates very acidic alteration. Whereas in Nevada, it might be a reason why there's not much for advanced argillic alteration in the Eocene, because these magmas were pretty SO2 poor likely. There wasn't much SO2 to dissolve in groundwater and form these big lithocaps. And in the high temperature, reduced gold skarn grading out to carbonate replacement deposits, but in a lot of cases gold-rich ones, and then grading out to distal disseminated with sericitic alteration. Some cases Carlin-type in that sense, but also in a vertical sense, Carlin-types when fluids evolve in that orientation, and that may be a more effective way to get more fluid into the deposit. And an important point is that probably all Carlin systems are not magmatic hydrothermal. I think there's pretty good evidence for some being that, in Nevada in particular, because you can form Carlin-type alteration, decalcification, jasperoid, with a whole bunch of different types of fluids, and you can transport gold with different types of fluids as well. So, these mechanisms were probably active all throughout the Great Basin over the last 250 million years. But in some instances where Eocene dikes are clearly associated with Carlin-style mineralization, I think there's pretty good evidence that they're linked. And the lower magmatic redox of the magmas results in an abundance of reduced sulfur, and that is just the optimal foundation to form that gold-rich metallogeny, especially when you're in reduced carbonates. Okay, and then the last slide, just to summarize here. toward a global Carlin-type exploration model, you likely need hydrous continental arc magmatism, a variation on that where magmas are reduced by carbonaceous rocks. This enhances gold solubility and extraction from magmas and optimizes gold transport to low temperature. Potentially tectonically neutral to extensional. This allows fluid flow to be optimized in the shallow crust. And then also abundant crustal meteoric water. So if you see shallow basins, coeval lake sediments, that's a nice way to bolster hydrothermal systems. And so you may suspect a Carlin-type metallogeny if high temperature deposits are gold rich or failed porphyry coppers, reduced intrusion-related gold or gold skarn systems, classic of the Tintina belt here. High temperature mineralogy shows reduced assemblages, pyrrhotite, arsenopyrite, bismuthinite, scheelite, and then lower temperature deposits are gold rich, silver poor, with pyrite, arsenopyrite, marcasite, and a trace suite of arsenic, antimony, mercury, and thallium. And this is just some of the areas that we put together, and this is in the GSN paper, but some of these areas that have characteristics like this, and some also have Carlin-type deposits. So, all right, and with that, I'd like to thank you for your attention. I apologize I went a little bit long. And I'm happy to take any questions now.
Thanks, Curtis. That was great. We've got one question in chat that says, in the figure showing cross sections east to west from Utah through Nevada, it looks like the crust is getting thinner to the west, but you have stated it gets thicker. Can you just, I guess, clarify that?
That's probably just me making figures incorrectly. It definitely gets thicker as you go west. The schematic cross section, yeah, it doesn't really show that. It more just shows the differences in the passive margin. But yeah, I should definitely clarify that in figures going forward. That's a good point.
No worries.
Along those lines, Curtis, of extension in Nevada and crustal thickness, what can you say about the Eocene arc and the crustal thickness then versus now? And did we have thicker crust in the Eocene?
Yeah, that's a good point. Yeah, the crust was much thicker in the Eocene, the Nevada plano. So that potentially had an impact on magma's ability to evolve and interact with the shallow crust. A thicker crustal column to dock magmas and interact, but that's probably part of the story as well, is the thickness of the crust.
Looks like Elizabeth Hawley has a question.
I have selected allow to unmute. Elizabeth, you should be able to unmute and go ahead.
Thank you. Thank you, Curtis, for a great talk, and thank you to you and Molly and Mike for organizing. I am a magmatist, so I absolutely love your story, and I'm probably bringing along a whole new generation of magmatists in my team at Colorado School of Mines. I do want to point out our work in the northern part of the Battle Mountain District at Marigold thus far. We really haven't been able to fingerprint an Eocene magmatic signature. It looks like Dante Hess will be showing some thermocron data that suggests that there is a heating event in the Eocene, but we're working on the stable isotopes. I'm wondering if you can speculate a little bit, because I think the elephant in the room is what's responsible for all the gold in areas where we don't see voluminous Eocene magmatism. Can your story help us out there at all?
Yeah, that's a good question. The obvious place that comes to mind is the Getchell trend, Turquoise Ridge, Twin Creeks. There is magmatism nearby, but yeah, it's not voluminous there. No, that's a really good question. I don't know. I think in that district, the dating is not, there's not much for dating of intrusions. So maybe there's more to the story there because there are intrusions around, but I don't know if I can speculate much on that relationship there. We looked dominantly, looking at districts where there was magmatism clearly associated, and there definitely are some where there isn't that. So maybe there's another mechanism.
Thank you. Well, I'll keep working on it. And I appreciate your
yeah, hopefully
it's really huge.
Figure it out.
Thanks a lot.
Yeah, thanks for joining.
Curtis, could I, this is Chris Henry, can I address that point a little?
Absolutely, Chris, take over.
I'm going to give, I'm not going to take over. I am going to give next month's Zoom talk, and I'm going to leave this a little mysterious at this point, other than to say that the lack of intrusions at the surface is not necessarily an indication of the lack of intrusions. And the Cortez area is a real good example. There are essentially no exposed Cretaceous intrusions, but combination of magnetic anomalies, alteration anomalies, drilling, and zircon xenocrust shows that the area is just packed with Cretaceous intrusions in the subsurface. And I think that I'm actually going to make a case for that next month.
Interesting. Yeah.
Chris, that was a great advertisement. I'm really excited. Thank you.
Yeah.
That's the plan.
Okay, Carly Balo has a question. I think Carly's still there, although I can't see you on my screen, Carly. The question to you, Curtis, from Carly is, were you able to get a spectrum of intrusion compositions to analyze for oxidation state from a single mining district in Utah? So did you have multiple samples from single mining districts that were pretty representative of various compositions?
Yeah, great question, Carly. So Bingham, we had all three major intrusions there. And Tintic would probably be the best example, where we had about 6 different intrusions, ranging from granodiorite composition all the way up to the rhyolites. So a number of different compositions through there. And that was, I didn't show it very well. I had to sort of move quickly, but you do see that the trend of at least staying oxidized through time. And it's not as detailed as we did at Phoenix, but that could be a really nice study. Tintic would be a good place to dive into more details there, but it looks like it's the same. Through time, it stays oxidized, and similar at Bingham as well, although we only had 3 samples from Bingham. So.
Great, thanks for that answer. It's good to know.
There is another question from John. I'm not sure who John is.
Hi, this is John Spurney. I didn't realize my full name wasn't posting. I'm calling from Costa Rica, but my early career was working around the Copper Canyon stock and sampling some of those jasperoids south of Antler Peak. And,
oh, very cool. Yeah.
We drilled out the Virgin Fault Zone there along up Galena Canyon for Barrick when they were still a junior.
Okay.
I've been left Nevada though for almost 30 years. And,
that's amazing you can join us. That's so great.
yeah, but actually I came back there 2 years ago to do some mapping out at Speedway, and then Mercer.
Okay.
Mapped on an iPad. My whole career I've worked on paper and clipboard, and I had to get trained. At any rate, I was just curious. Marigold's gotten so big along such that almost 6-7 kilometer trend north-south, and it seems like those structures are kind of striking south towards the Copper Canyon stock. I'm not sure whether you've looked at that, but
whether they're related. Yeah, I think they're probably unrelated in terms of like the actual same intrusive episode at Copper Canyon versus Marigold, but the
so distant.
Yeah, because there's a number. Caleb King's work in the district, Battle Mountain District broadly, showed about a dozen different Eocene intrusive centers, sort of all right around that 38 to 39 MAH, and some of them have big alteration assemblages and mineralization associated with them, and others don't. But yeah, maybe Elizabeth Hawley and company will be able to figure out more with Marigold and what that's related to. But they're probably discrete systems.
Well, there's also Trenton Canyon in between.
Right. Yeah.
Yeah, my memory's a little less clear than it was 24 years ago or something.
Do you remember much about the South Antler jasperoids? I've been really curious to talk to somebody who had worked those there. Are they relatively enriched in gold, or?
Yeah, some of them had over, I think, 40 grams gold. Santa Fe drilled one of those too. They were always rootless. We never found anything beneath them. I mean, the Barrick has all the data from the drilling there. It was all RC drilling on them. I think it was 87. And there was one I remember that was really silverish for some reason. It was an oddball, different looking rather than a sort of light brown. Sometimes had phenos of barite in it too. But this one had very high silver, I remember.
Interesting. Yeah, that's pretty cool. Yeah.
Still have the actual, some of the paper ones. I might scan them, send them your way if you're interested.
Oh, I'd love to. Yeah, I'd love to take a look at that. That's neat.
All right. Well, thank you.
Any other questions for Curtis? All right then.
All righty.
Well, Curtis, I think you're off the hook now.
All right. Well, thank you everybody for
Say hi to everyone.
taking the time to listen.
Yeah, great presentation. Thank you.
Thank you.
Thanks a lot, Curtis. That was great.
Well done, Curtis. Thanks very much.
Thank you. All right.
And just a note for everybody, we'll be posting this and all our virtual lectures for the symposium on the symposium website, which is www.gsnsymposium.org. So you can go there and listen to Curtis's talk as many times as you'd like. And, thank you all very much for attending.
Yeah, thank you.
Nice work.
Thanks.
Good job, Curtis.
Yeah, well
Thank you.
done. I really am gonna go watch it again. I'm damn need to hear it like 3 times.
So you can fall asleep later.
I mean,
Yeah. Yeah, it's actually it is the silver lining of this of the current coronavirus situation. There's so much more content available to watch from other people. I've learned a ton in the last few months from that. It's been great.
because it's really nice. It's easy to. I mean, I let them play while I drive. It's so good.
Yeah, it is. It's great.
And you do a fair amount of driving, don't you, Molly?
Lately, I do. I don't normally mind it. Eric, are you on here? You got anything we need to follow up on?
No, I'm on. We can follow up later. Just make sure we're talking the same schedules.
Perfect. Well done.
Alrighty.
Yeah. Molly and Curtis, are you going to make the planning meeting tomorrow?
I don't think I can make it tomorrow. I may, if I can get out of a few things. I might be able to call into it. But.
I'm going to be out at Battle Mountain, speaking of Eocene magmatism, so
Yeah.
I won't be able to make that meeting.
Let me make a note. I should be there. I've got someone to come look at core, but I should be able to hop on. It's at 3 o'clock. Okay.
Yes.
Yeah. Okay. I'll try and get on at 3. For sure. So I'll be there.
Okay, perfect. Thanks, Molly.
All right.
All right. Thanks.
All right. Thanks, guys. We'll see you later.
Yep.
Okay,
Bye.
take care.